Suraj, please unmute your microphone.
Hello everyone. Namaste. Good morning, good afternoon, and good evening. Well, it's late afternoon here in Nepal. It's GMT plus 5:45. I hope you all are doing good. This is Suraj Gautam, a civil engineer and a DRRM professional from Institute of Himalayan Risk Reduction, and I'll be your host for today's session. First of all, I would like to welcome you all to our very first session of our third webinar on disaster risk reduction. The theme for today's webinar is Geo-Hazard risk assessment where we would be talking about the ground experiences and number of initiatives and about the different measures of risk assessments. So on behalf of the organizing team, we are really grateful to our speakers who will be sharing us with their insights and healthy experiences. So we'd like to welcome our speakers. Our first speaker is Dr. Mohammad Safiq, who is Associate Professor at National Center for Excellence in Geology, University of Peshawar, Pakistan. Similarly, we'll be having second presentation from Dr. Anand Pradhan, who is a Senior Divisional Engineering Geologist at Water Resource Research and Development Center, Nepal. So the session will be moderated by Assistant Professor Dr. Basanta Raj Adhikari from Institute of Engineering, Tribhuvan University, who is also the visiting scientist of Institute of Himalayan Risk Reduction. So it is indeed an honor to have insights from our distinguished speakers. Also, we'd like to welcome all of our participants who are attending this session. We are very pleased to share our graphs of webinar registration, which has been increasing in a very healthy rate. Our webinar event is also featured in the prevention website and on the prevention website, and we have had a registration of 117 on the very first day of release of our webinar poster. And till date, we have 337 registrations from different corners of the globe. So to address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction, and we'll be receiving the queries and feedback from our Zoom chat box as well as from our social media live stream. So this webinar on disaster risk reduction is organized by Institute of Himalayan Risk Reduction, and it has been done on a regular basis. So we believe this webinar series has definitely been supporting all our early career scientists, DRR professionals, professors, and all the participants. And yes, it is just a beginning and we'll have a long way forward. So let me share some brief introduction of our Institute of Himalayan Risk Reduction, what we have been doing. So I think it's visible. Okay. So Institute of Himalayan Risk Reduction is a research institute established with an objective to assess and understand the risks to contribute to the sustainability. Complying with the Sendai framework for disaster risk reduction, IHRR envisions to understand the risks and applications of interdisciplinary knowledge with science, engineering, technology, and innovations to contribute for risk reduction and bridging of academic research with professionals and policymakers for the sustainability. So in our team, we have professionals with expertise and experiences in the field of DRR in understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. So we have collaborated and we have successfully accomplished a number of projects that includes recently we have also collaborated with the Ministry of Health and Populations, and for this COVID-19 response, we contributed our part in developing an information portal and Hamro Swastha mobile applications, which has been widely used. Similarly, we have also collaborated with local government to bring out some frontier technologies such as UAV surveying at Hetoda sub-metropolitan city for the very first time. Similarly, we have had a quite number of engagements that includes organizing a transboundary hazard projects, working in different sectors. And we are also advocating to the recently promulgated DRRM Act and trying our best to collaborate and contribute. So this much for the introduction. Now I would like to share some house rules for this webinar.
Yes, can you just close the slide? Someone is annotating over there.
Okay, sure. Sure. Uh, the house rules for this webinar are the audio and video of the participants will be switched off. For any queries, the participants can write up in the chat box or in the comment section of Facebook streaming live. The waiting rooms has been enabled. Only the registered participants will be allowed to enter the room. Also, I would like to request our participants to please rename their name as mentioned in their registered link. So feedback links will be provided during the session, and we'll be giving uh, further, we'll be giving we'll be creating some options to to share the questions even by sharing the video. So feedback links will be provided, and the themes for today webinar is Geohazard risk assessment, where we'll be talking more about the Geohazard risk assessment, and it is really relevant as you can see the data of, I'm talking about the Nepal. If you see the data of 2020 alone only, as per the MOHA source at the DRR portal, there are more than 183 death tolls till date. So we have to invest a lot on this geohazard risk assessment. So without any further delay, I would like to move on to our session. And may I request Dr. Basanta Raj Adhikari to moderate, to proceed further with his moderation. Thank you for now.
Thank you, Suraj. Am I audible?
Yes, you're audible, sir.
Thank you, Suraj Gautam, Executive Director, Institute of Himalayan Risk Reduction, Nepal, Kathmandu, Nepal, and I'm very pleased to moderate this session for today. And today, as Suraj already explained, that we have two esteemed colleagues from Nepal, Dr. Anand Pradhan, and from Pakistan, Dr. Mohammad Safiq. Both are my friends, and we have been working for a long time, more than 10 years in the Hindu Kush Himalayan region. So I would like to request our participant to post your questions in chat box, as Suraj has already mentioned, and then also to our presenters, when you share the slides, please close the annotation so that participant will not disturb during the presentation. So the first presentation for today will be by Dr. Mohammad Safiq. He's an associate professor at the National Center of Excellence in Geology, University of Peshawar, Pakistan, and he's currently doing on the natural hazard assessment in the northern Pakistan. And his mainly research focuses on geohazard assessment, mainly earthquake, landslides, and the long-term hill slope evolution in that part of region. And we are very pleased to see his recent publication in geomorphology about the landslides, temporal variation, spatio-temporal variation of landslide after 2005 Kashmir earthquake, and which is widely renowned, and not only in the Hindu Kush region, but also around the globe. So we have requested him to give a presentation, and he accepted our invitation, and I'm very, very pleased to invite him to give a presentation on geohazard risk assessment, monitoring, and mitigation in the northern Pakistan. So Dr. Safiq, the virtual room is yours. Please, you can start your presentation.
Thank you very much, Dr. Basanta. I'm personally thankful to the Institute of Himalayan Risk Reduction for giving this opportunity to share some of our ongoing research on the geohazard risk assessment along the Himalaya region in the northern Pakistan. I will start with my presentation because it's not a very specific study presentation, but I've tried to cover some different topics. So I will go through them, but generalize. So I'll not go in more detail. But if there are some questions, I will surely be able to take the questions. So it's a generalized presentation. Some of the stuff that we did actually after the 2005 earthquake. Okay. Can you see the slides now? Can you see the slides? Okay, I hope so. Okay, so the title that I have selected is Geohazard Risk Assessment, Monitoring and Mitigation in Northern Pakistan. I'm Shafique, and I'm from the NCG University of Peshawar from Pakistan. Probably some of the very common reasons of the very frequent geohazard in the whole Himalaya region that actually are common for Pakistan, for India, for Nepal, parts also for Bhutan, even also for some south part of China. These are common everywhere. Like we have the active tectonics, the whole Indian plate is moving towards north with some rate of 31 millimeter per year, and that is causing a lot of stresses in the Himalaya region. And so because of that active tectonics, we also have the frequent earthquakes there that cause other secondary hazard damages. The topography is quite rough. You know, there are steep slopes. We have high lofty mountains there that also trigger a lot of other hazards. So climate is also one of the big trigger for these hazards. Like we have mostly the monsoon season in that area where you have all the rain in concentrated in one or 2 months. So you have most rain in couple of months, and then the rest of the year is relatively it's dry. So that also intense rain in few months also trigger the different hazards. And then we also have the human interference. Also, human is also contributing to the different hazards there, like the intervention into the natural environment, where we actually disturb the natural environment, the natural balanced environment, and we trigger the geohazards. I can see also some picture that I've shown here, like they are building a road on the very fragile slope. So if you build a road, basically you're disturbing the natural slope, and that also triggered the lands and also the hazards. So now I'll start with the seismic hazard assessment as the first section of my my presentation. So where I would touch upon some of the stuff that I actually did during my study, during my research. So what actually happened in seismic hazard assessment, that just to give you, okay, this is the slide that I have selected actually for Kashmir earthquake. Probably Dr. Masanta already talked about it, that we had a very big earthquake in 2005, like 15 years before from now, but we still remember it because it was a very big event in Pakistan. Also in the whole region, it was a very big event from the seismic point of view. It also leaves a lot of lessons, a lot of information for us. It was occurred on 2005, earthquake 2005, magnitude 7.6. It killed actually around 80,000 people at that time, and then also a lot of economic damages. And the distinct character of this earthquake was, we saw that there were very spatially varied seismic response. Like some area has received high ground shaking, and some area received actually relatively less ground shaking. That also leads that impact was visible on the building damages also. Like some building were completely collapsed, some were at least damaged, some were completely standing. So the situation was spatially very variable. That give an indication that something happening in the subsurface that leads to this spatially variable seismic response. And also there was very long widespread the landslides were there. We saw thousands of landslides happening in the triggered by this earthquake. Actually, this region was already prone to geohazard, like earthquake and also landslide. The region was already having lots of landslide in that region, but earthquake really triggered them a lot. So after the earthquake we have found actually there were thousands of landslides that were triggered by the earthquake. Now, as I mentioned, that there was spatially variable seismic response, and that can be seen here in the build damages. This is a picture taken after the earthquake. If you see the building structures, it's almost same. There's not significant difference in the building structure. It's mostly more or less it's the same structure that had been built in that region called Balakot, which very intensely damaged by the earthquake. You can see that some of the buildings are completely collapsed, like they were completely collapsed. A lot of casualties happened there. While some buildings were still standing, but they were damaged. Like you can see these buildings here, the yellowish, also the bluish. The building is still it's surely damaged. There were big cracks in that building, but at least it was standing. So people who were inside, at least their life were safe. And there were some buildings which were completely undamaged. Surprisingly, they were completely undamaged. Like there was no damage, there were no cracks, and they actually survived during this whole earthquake. And they are still there at the same structure. These buildings are still there after 15 years. They are still standing there. Even after the earthquake, we had a lot of many aftershocks, but those buildings were, stable, and they are still stable there at the same location. So you can see that the impact of the earthquake and seismic response that can be very spatially different because of the subsurface. Like the feature subsurface actually has a very significant impact on the seismic response. And another picture also of the same earthquake, same information, like some buildings are collapsed, some are structured, some are standing but damaged, and some are completely undamaged. This is one of the building that I want to show here, specifically this building that are there. It's actually it's a shopping plaza, double story shopping plaza. This is the building that only building in the whole region which were completely undamaged. There were very minor cracks, but they are repaired. So this building was the only building in the whole region which was survived, and the rest of all the building were at least damaged or some are already collapsed. So this is very unique information that we can see, and some that tells us that something is happening also in the subsurface that leads to a spatially variable seismic response. Okay, now what actually, for some of the students that are maybe here in the webinar, I will just give you one slide where what actually happened during an earthquake and how that leads to variable spatial response on the surface. So when earthquake happens, probably you all know about it. We have a hypocenter from where the earthquake is generated, and then we also have the fault from which actually triggered the earthquake. So that the feature of the fault, the thickness, the depth of the hypocenter also has an impact on the seismic response. Like if you have a shallow earthquake, you expect more response, more shaking, and if you have a deep earthquake, the response would be relatively lower. Same with also with the fault structure, like you have different types of faults and the different nature of the fault, and that also have very significant impact on the magnitude of the seismic response that we are receiving at the Earth's surface. Now, so you have a source impact, like the source of the earthquake, and then you have the medium, what we call medium impacts. The medium is basically when earthquake happen, it generates different kinds of seismic waves. We know there are primary waves, there are secondary waves, and those waves when move through the earth, through the medium, like the subsurface, the subsurface medium has also very significant impact on those waves. Like if the waves move through hard rock, the impact will be different. If they move through a soil, the impact will be different. So that medium through which seismic wave also passes or transverse through it has also very significant impact, and we call them the medium effects. And people actually model them through the what we call attenuation model. If you heard this term, attenuation model are being used, which actually just look at the distance between the source and the site, and then they calculate the amount of ground shaking that can be received at some point. And then when these waves arrive at the Earth's surface, then we have a different kind of topographies, we have different kind of geologies, we have different kind of the soil thickness, and that also has influence on the magnitude of the ground shaking at the Earth's surface, and we call them the site impacts. So these three are the major impacts which actually which quantify the amount of shaking that we are receiving at the Earth's surface. And these things are varied, right? The site effects actually is controlling the magnitude of the earth received, the magnitude of the ground shaking received at the surface. That is varying because the site factors like the soil thickness, the soil material, the moisture content, they are varying at every location. After a few meters, you can see things are varying. The soil is different, might be the chemical composition might be different, the soil thickness might be different. So these different features on the Earth's surface actually leads to spatially variable ground shaking. That we can see also in the damages. And what we actually did that to looking at the impact of the site impacts, like the different kind of soil thickness, we tried to model the soil thickness in the whole that big district, what we call it Muzaffarabad and the Balapur, which were severely hit by this earthquake. So we tried to model that, like how we can model it to see the spatial variation of the regular thickness in the whole region. And you can see, okay, this is medium impact. I'm just showing this impact with the cartoon. Like if you have a very nicely built road and you're sitting in a very modern and fully equipped and full specs car, and the car would move at very high speed, and also you don't feel any jumps, right? You don't feel any jumps. You're sitting very calm. There's no movement, right? Everything goes very perfectly. But if suddenly that car enters from a very nicely built metal road to unmetal road or the crampy road, what happens? You feel these shakings, right? You feel these jumps of that car. And this exactly happened in terms of the seismic waves. When these seismic waves basically enter from a medium of higher velocity, like the bedrock, into the medium of a lower velocity, like the soil, or we call it the regolith, what actually happened that the velocity is decreased. The velocity of the seismic wave is decreased, and the amplitude of the wave is also increased. And because of this variation in amplitude and seismic waves, the impact on the surface is different. Usually, if you have built your house on a bedrock, it will be less affected by the seismic waves, right? It will be relatively safe. But if you build a house on a soil, which is very deep soil, the impact would be higher because of the less shear velocity of the wave and also the high amplitude of the wave. The impact would be higher on soil compared to the on the bedrock. So to model the soil thickness in the regular in the whole region, we know that there are some proxies that we can use to model them. We cannot measure the soil thickness at every single location after every meter. That would be practically impossible for a bigger area. So we try to actually look at the proxy, the variable which control the special variation of the soil thickness of the regular. And we know that topography, like if you have a steep slope, the regular could be less surely because it will slide down if you have a steep slope. And in the basin, normally in the flat area, we have a higher soil thickness, which actually because of the flat terrain. So topography has an impact. We know the geomorphology has a very big impact. Like on the river terraces, you see the very higher soil thickness of the regolith. While if you go for alluvial fan, you will have higher thickness. But in the flood basins or in the active flash flood basin or the active flood basin, the soil would be very less. So the geomorphology also has a very big impact on the variation of the thickness. The geology we know, the land use also has a big impact, like how we can use the land use. And then so this is a factor that we can model from the remote sensing very easily. We know all the data is already available most of the time. And we can also build some of the data from morphology and the land use. We can build them from satellite images. And this data can be used to build all these parameters. So we have actually collected these parameters. And then we divide our area into landscape. Like if you have a valley, in the valley you have a depositional landscape like the valley basin, and on the surface of the valleys you would call it the erosional landscape. So from where the material is being eroded down and it's being deposited at the valley base. So we have tried to, because there is a very big variation. Like in the basin you have very high deep soil, while on the surfaces or on the steep slope it will be less. So we try to model them differently, like the depositional landscape and also the erosional landscape. For the depositional landscape, we have selected three predictors to model soil thickness. First one was the landform, because this is what we have observed, that landform has a very big impact on the variation of the soil thickness there. We have mapped them in the alluvial fan, flood plain with the river beds and terraces. Then we have elevation. We also know elevation has a very big impact. Like on the higher altitude, usually you have a less thickness, and also distance from the stream. Like if you move away from the stream, the thickness was increased in some of the cases. And then we have collected some points actually to some samples of the actual measurements of the soil on the depositional landscape. So some area, like these are the outcrop on the first picture, like in A, we have an outcrop, so we can easily measure the thickness of the soil from the river base to the top, and there's one more sample. And then we also have a big problem that, because if you move away from this outcrop and you want to go like 100 or 200 meters up from the you have to make a digging, like really deep digging, like 20 or 25 meters. But we can't do that as a scientist because we don't have a lot of resources to do the digging, to do the borehole, or do the digging to measure soil thickness. So what we actually did, that we tried to use other technique called geophysical techniques to measure the soil thickness at the area which were unexposed, or where the soil thickness were unexposed. So we have used actually the electric resistivity as one of the efficient technique which people actually using out for the soil thickness. We use that technique to take the profile on the area which was very deep, and then try to measure the soil thickness in the area. And you know, it's very obvious. We all know that the resistivity, the electric resistivity of the rock is higher. It's higher than the resistivity of the water, because the current can pass, the electric current can pass very easily through the current, through the water content. Like if you have soil, then the resistivity would be lower, and if you have a hard rock, the resistivity would be higher, right? So we know that from different literature, it's already obvious. So we have selected the sharp contrast, the sharp boundary of increasing the resistivity from lower to the higher as the contact between the bedrock and the soil, right? So if you look at this, so this is our hypothesis, that where they have where the resistivity suddenly increase from lower to higher values, that is the contact between the soil and the bedrock. And you can see that in the first slide, on the first profile that we selected from the resistivity, you can see that the resistivity increased at this point, this dotted line indicates that this is the boundary between the soil and the bedrock. The depth was 1.68 meters, and this black arrow shows our interpreted thickness, and this blue arrow actually shows the actually measured soil thickness. So you can see that this is a very close association between the predicted one and actually the measured one. And same here also. There's a sharp contrast between the higher and lower resistivity, so we'll make them as a boundary. And here also, this could also be this is actually the point where we have mapped them as a thickness of the soil. So without actually doing any digging, you can use the physical techniques to measure the soil thickness. And then we have to also try to verify them with our actual models, with actual measurements, and we saw this very close association. So we use the resistivity actually at the location where the digging was not possible, the outcrop was not visible, so we use that one as to estimate the thickness. And then we use some sample, we do some statistic on that to model them. And you see also correlation is there, like if the river terrace is also the number is changing, like if you move away from the soil are going close to that, the thickness is also changing. So we apply simple regression models. They're available and the literature also on the different internet website. You can see that very easily. These are basic stuff, and we use that to build a model that we can use to measure the soil thickness and to model it on a bigger scale. And we got a very good correlation between measured and the actually predicted soil thickness. Here's the map that we have actually modeled the soil thickness from 0 to 24.05 meters actually. Now the equation was higher, and then we have to also model it on the erosional landscape. Like we actually applied the same. We collected some sample, our 200 sample were collected on different slope classes, on different elevation classes, on different aspect classes, and then we have tried also model, compared them with those independent variables to apply the regression model and then map the thickness on the whole areas. You can see that here. We have different geological formation, and on different geological formation, we are seeing actually different variation of the soil thickness, which show that there is a big impact on the modeling also. And here is also so this is the modeled soil thickness on the erosional landscape. So we combine the erosional and the deposition, and this is actually the final product where we have actually modeled the whole soil thickness in the whole area. Then try to verify them, to see the impact of those model soil thickness on the building damages after the earthquake. We try to correlate them, like to see if a house is built on a deep soil, how the damage is, and if this building is built on a shallow soil, how the building is, like what was the response of the earthquake on the buildings. And we have observed that generally, generally the houses which were built on a deep soil, they were more damaged compared to the houses which were built on the shallow soil. Of course, there are houses which were built on the shallow structure, shallow soil thickness, but they are collapsed. And the reason is also that that's not the only reason. Is not the soil thickness is not the only reason. There are multiple other reasons also: the building structure, the building design, the age of the building, the material of the building, the geology. So there are also multiple other reasons also which also determine the damages of the building. So, but the soil thickness is also one of the factors which contribute to the damages of the building. We actually published these results into these two papers. I can share them if someone is interested, and they can read that whole process that we did for this modeling. Okay, there's another study that we also did on the mapping the shear wave velocity. I have discussed before also in the previous slide that if the velocity the shear wave velocity is lower, the seismic velocity is lower, the damage would be higher. And because of the high increase in amplitude, and also the time of the shaking will also be higher. So we have applied this also here in one of the studies that we did. Actually, we simply used the digital elevation model. There were papers published already by the group from USGS. They have correlated the terrain slope and elevation and different geological factors, morphological factors with the shear wave velocity as one of the proxies for the modeling it on a regional scale. So we have applied simply a digital elevation model that was available free of cost for the whole world. We have applied some OBR techniques, object-based image classification techniques, to model the geomorphological units in that area. We actually modeled the geomorphological unit, and then we applied the known model numbers for that region in that for to model the height. So this is our final product from the orbit-based image classification, and the final map was published here. So this the red zone actually shows the basin where the seismic velocity should be lower, and that's because that these are the regions which are prone for the amplified seismic response. This is what actually we also observed in 2005 earthquake, that after the earthquake, the velocity was lower here, and that the damages were also higher in these basins. Okay, now moving towards the landslide section here. So we also currently I'm working on the monitoring the landslide after the 2005 earthquake, because there were a lot of studies available which predicts that after the earthquake, the landslide norm usually gets stabilized because of the natural process and also because of the natural healing process. So these are stabilized, and there are studies like in Winchuan in China. There was a paper which claimed that they claim that most of the earthquake, most of the core seismic landslides are being stabilized 10 years after the earthquake. So we also tried to see how the landslide triggered by this earthquake, or what is the status right now after 15 years of the earthquake. Okay, we have actually, usually you can see that we have we build different inventories, like different temporal inventories. One was taken before the earthquake, and second was taken after the earthquake, quick after the earthquake, and then we also selected the inventories 2010, 14, 16, and 18. So we look at the dynamics of those these landslide till now, 13 years after the earthquake, how they are, what is the status of those landslides currently after the earthquake. And we can see that even from this inventory that the area is decreasing. The landslide that we actually map, the numbers is decreasing, and even also the area covered by the landslide is also decreasing. We also look at the different types of landslide. What is happening with different types of landslide, which were actually triggered by the earthquake, and what is their status right now? So we have actually built up these inventories from the satellite images which are available easily. And then also with some field information, with some field verification, we have built this temporal inventory. And some of the statistics, which is available in the paper that I will show the link. Okay, here is the results. The general results, like the area differences. If you look at before the earthquake, as I mentioned, also this is the region which was already prone to a landslide before the earthquake. So we already had a landslide in that area before the even earthquake happened. And what happened even soon after the earthquake, like here in 2005, when the earthquake happened, the area jumped significantly from 6 to even like almost more than 3 times. The landslide number is increased, the landslide area is increased. But then gradually we can see that the landslides are wishing the stabilizing trend is being seen here. The trend was relatively slower in the first few years. Like if you look at it from between 2005 and almost 10, the trend was very lower, because we know that if earthquake is triggered, and then we also earthquake was triggered in the 2005, and after that we had next year we had a very intense monsoon season. So the area was already unstable, and then you see a lot of rainfall happened. So the landslides which were not even triggered at that time, they are triggered the next year by the intense rainfall. So because of this rainfall and the fragile slope, which were unstabilized by the earthquake, we were seeing very slow trend of stabilizing those lands up to 2010. But after that, when the loose material is already being eroded by the rainfall, by the landslide, we saw a very sharp decline in the landslide between 2010 and 2014, because the loose material was already eroded by the rainfall. So after like 2010, from 10 onward, we see very sharp decline in the landslide area. Even the monsoon were there. They were even more intense in one of the year. I will show the rainfall data right now. But the area is decreased, which actually indicate that the landslides that were triggered solely by the earthquake, they are being stabilized. But the landslides which were present there before the even earthquake, they are still active there, and they are still currently even they are still active in that region. And the trend is currently even decreasing. Like we can see that now, almost like it took almost 13 years to arrive at the level of the pre-earthquake. Like they were 6 kilometers before the earthquake, and now we also if you're touching the 6, maybe right now after 2 years from 2018, maybe the area is being reached to the pre-earthquake level. So in case of Pakistan, like it took almost 15 years for earthquake to arrive at the pre-earthquake level for the core seismic like landslide, which is different than the other studies which predict that usually after 10 years after the earthquake, the landslide landslide area is reached to the pre-earthquake level. So this is different results here. I will show the reason right now. There's a very interesting reason here. Here's the rainfall data that we actually overlaid the data of the earthquake on the lands. On the rainfall in the background, we have a rainfall. And these months of June and July, which are usually the monsoon season, they have intense rainfall. And that's why we see also, so the rainfall was higher even in these remaining years. Well, look at the 2010, we have very intense rainfall there. And also 2012, the rainfall was very higher, but still the landslide area is being reduced. And this is what actually we try to see how the landslides are spatially different. Like some of the area are extremely active, like they're still active, which means extremely active means actually that they are active from the 2005, even before the earthquake they were active, and current till now we see them still. These are active landslides, so we map them as a extremely active landslides which are still even present there. Now, the reason for those delayed stabilization or higher landslide activity in that region is also the human interferences, the anthropogenic factor that we discussed before, that the humans are also contributing the triggering for landslides in that region. These are some of the landslides that I'm showing here, and here surely they were triggered by the earthquake. These landslides were triggered by the earthquake. But when people saw that the material, the bedrock can also be used for construction material. It's a limestone, which people are using there for the construction material, for building their houses, also for other purposes, mainly for building actually the houses. People are using this material. So then there are small companies, small builders which came in, and then they started the digging of those or the excavation of those material from those landslides. And because of those continuous excavation, the landslide area is increased. And this is also these are the big landslides that trigger, which were currently mainly triggered because of the human factor, like they are doing digging there, and because of the digging or the excavation, you are actually losing the whole mountain. The stability is also decreased and that's why you see these landslides are still active in that region. We also try to see correlate these like the active landslide with a factor like the topography, the environment, to see which is the area where we are still seeing extremely active landslide, and what are the reasons behind that. We try to correlate that with the elevation. You see the elevation, this part of the region, like between 1200 and 1600 meters, where it's continuously receiving higher landslide. And similarly, also this terrain slope of 30 to 40 degrees are receiving higher landslide in that regions. And similarly, also this slope south aspect, southwest, and west aspect are receiving higher landslide. And also we have, but one factor that I want to highlight here, that we have also seen in the region that these higher, like the vulnerable elevation classes, vulnerable slope classes, and also vulnerable aspect, also the region also where the earthquake fault was present. So this is some of the area where these all factors are combined together, and because of that, we have very active landslide in that specific region. So these some of the factors where these different factors are combined at one point. Like you have a in the same point you have a same elevation, like this vulnerable elevation and this vulnerable slope class, and also this vulnerable aspect, and that's why these are very intensely affected by the landslide. We also try to look at the impact of revegetation, like what happened with the vegetation, because after the earthquake, we can see this from the graph here. This is actually NDVI results. After the graph, you can see that after the earthquake, the amount of vegetation is also being affected very significantly. Like there's a sudden drop in the vegetation area after the earthquake, but that's also catching up now. Like the lands there, we see revegetation, right? Regeneration of vegetation which were affected by the earthquake. We see it now in that region also, that the revegetation is increasing, and because of the revegetation or regeneration of vegetation, we are seeing that the landslide area is also being decreased. And this is the paper that actually we published this result in this recent paper just published this year. Okay, some quick 2-3 more aspects, and I will stop. We have actually also monitored the landslide in one of these big affected area. We have used a time-lapse camera, which we actually mounted on in this cage, and the camera was looking at the landslide in the background, and we have programmed the camera to take two pictures every day, and this was there for many years to picture every day, and then we tried to model the variation in the topography in the landslide after the earthquake. And you can see the picture taken at different years and different times, and then we have analyzed them to see which actually portion where we are receiving the more deformation of the landslide. Here are the results. The pinkish area are the area where we are seeing a lot of deformation of the landslide because of this quick rainfall and also other factors. We also use some UAVs in another area to see the deformation also. So we have taken some temporal pictures, temporal data with the UAVs of one of very active landslide. And you can see that we have actually applied the techniques of the Cozy Core. People are using that very frequently to see deformation, like pre and post events images. And you can model actually the direction of the movement. Also, you can model the direction, also the magnitude of the deformation in that region. See also here, so we're actually seeing the impact of these different times on the deformation and direction of the movements. Okay, we also use the OBIA to map the landslide automatically, relatively called semi-automatically. We have tested the technique in one of the region in Muzaffarabad, and we are seeing some good results. Like we have to look at we have automatically, semi-automatically, I would say, map the landslide. So this can also be used for and the alternate for the actually manual digitization, which usually take a lot of time for the landslide. So this is end from my side. Thank you very much. I'm open for taking any questions. This is also my email address is there. So I will still present. I will listen to the next talk, and then I will be willing to take if there's some question also there are comments. Thank you very much.
Thank you, Safiq, for your wonderful presentation and using these latest technologies for understanding the landslide distribution on spatio-temporal way in the northern Pakistan. I'm pretty much sure that you are also working on this Karakoram highway, which is also one of the important route for Pakistan to connect China. And we heard that there are lots of landslides due to after this earthquake and due to other triggering factors. And there's one interesting lake, the Chaptabad Lake, and there's so lots of interaction over there in that region, and the Gilgit, which is very beautiful valley, and Hunza. I want to visit once in my life to Hunza because I have read a lot about Shangri-La, and I want to be there.
You're most welcome.
And yeah, thank you, Safiq. Please stay with us, and please look into the chats box. There are some questions to you.
Okay, I'll take.
We'll take later on after another presentation. Thank you very much once again. And so the next presenter for today is Dr. Anand Pradhan. He's a well-famous researcher in the field of landslides, not only in Nepal, but also in the other part of the globe. Currently, he's working as a senior divisional engineering geologist in Water Resource Research and Development Center under Ministry of Energy, Water Resource and Irrigation, Government of Nepal. He has completed his PhD from Pukyong National University, Busan, South Korea. His scientific interest lies in the spatial prediction modeling. They're being primarily applied in the framework of natural hazards. And moreover, his research focuses on combined physical-based and statistical methods to predict landslide susceptibility from an initial interest in rainfall-induced landslides. He has recently switched his attention to the combination of co-seismic landslides, or the landslide triggered or landslide happened after the earthquake, and rainfall-induced landslide prediction. And he has been working continuously in this field more than 15 years, and we are working together, and he's our go-to person. We always ask something if we don't have any solution, so he has the solution on this head of landslide prediction and others. So today he's going to give on his talk on prediction and assessment of rainfall triggered landslides, rainfall threshold, susceptibility, and vulnerability. So Dr. Pradhan, the virtual floor is yours. Please start.
Just a moment. Can you see? Can you see my PPT? Hello?
Yeah. Wait. Have you shared the slides already?
Yeah, yes. I don't know, something is...
Wait. You are co-host, right? Yes. So you could... No, we don't see your slides.
Okay, just a moment.
No. Okay, wait.
Yeah, it's coming now, I guess.
Yeah.
Oh, yeah, okay.
Okay, good.
I'm very new in Zoom, you know.
Yeah,
Okay.
everything is all right. You are audible, visible, and you can see your slides. Please go on, Dr. Pradhan.
Okay, thank you. Thank you so much. Thank you so much, Professor Basanta, for introducing me. Good afternoon, everyone. And namaste from Nepal. First of all, I would like to thank the organizer, Institute of Himalayan Risk Reduction team. Yes, you guys are doing an exceptionally good job by gathering different experts in the geoscience platform. Hello, I am Anand Pradhan. I'm working as a senior division engineering geologist in Water Resource and Resource Development Center. Yeah, today I'm going to talk about the prediction and assessment of rainfall triggered landslides, rainfall threshold in Nepal Himalaya, and susceptibility and vulnerability assessment. This is my content of the presentation. It will start with a topic like landslide better. Why landslide better? Nepal every year. Then I will show the trend in landslide in Nepal Himalaya, followed by rainfall threshold and landslide susceptibility and vulnerability assessment. And I will wrap this presentation with some conclusion. Actually, I'm working in Nepal Himalaya since last year. Actually, now it has been completed just 1 year, so I don't have the big batch of data, the big bunch of data from Nepal Himalaya. So I will show some case study from my previous work, like in Korea and in Colombia. So I will start the content, first content, why landslide better Nepal every year. It's like because of rock topography and climatic condition, Nepal becomes one of the most disastrous prone countries in the world. It ranked 4th in climate change impact, 11th for earthquake, and about 80% of the total population in living with some kind of natural disaster. Nepal is susceptible to man-made and natural disasters. Now you can see from this graph, yeah, this is the data from 2010 to 2019. There is more than 1,000 people were died during the landslide. And second is the thunderbolt. A landslide is the major disaster in Nepal since couple of decades. Here, the landslide play a fundamental role in evolution of the landscape in tectonically active mountain chain. Now you can see the Himalaya is the product of collision between landslide and erosion plates, and the rock of this tectonically active zone is in strain condition. And in tectonically active region, landslide play a fundamental role in the evolution of the landscape, providing a mass balance mechanism. This graph shows the mean monthly precipitation in 3 zones adapted from Talsa Badal et al. 2018. This blue line shows the mean monthly precipitation of whole country. Most of the precipitation concentrated in monsoon, season. About 80% of the annual precipitation occur in this season. Landslide constitute of major natural hazards in Nepal, mainly due to the unique combination of active tectonic zone, tectonic setting, high rate of weathering, and abundant rainfall. Climate change impact the rainfall pattern. Nepal also experiencing the short duration and high intensity rainfall. Landslide constitute a major natural disaster in Nepal, mainly due to the unique combination of rock topography, active tectonic zone, and high rate of weathering and abundant rainfall, and adverse geological condition, and concentrated heavy rainfall. So you can see here the trigger factor of this landslide is the intense rainfall, and in Nepal, the short duration and heavy rainfall, high intensity rainfall is concentrated in the monsoon season. Now, this is the result, and this is the result of such unique combination during monsoon season. Such type of news headlines and front page of the such kind of news covers the headline and front pages of the newspaper. A similar catastrophic noted each and every year. However, the community did not learn lesson from what that event and settle on the debris fan of the earlier flow and steep slope. In the hills, deforestation, on-plan settlement along the slope, haphazard road construction, and improper land use for farming and human settlement lead to the landslides. Now, I would like to talk about the trend in landslide occurrences in Nepal. In recent years, it has become apparent that landslide represent a far greater hazard globally than had been previously assumed, both in terms of economic losses and fatalities. For landslide studies, historical landslide data collection is important, which helps us to set the trend and preparation of rainfall threshold warning. Recently, we are able to collect historical rainfall induced landslide catalog. In the complete dataset of that landslide catalog from the period of 1970 to 2019, we have recorded a total of 2,488 fatal landslides in Nepal, which caused 3,212 recorded fatalities, representing the average of about 36 deaths per year. The temporal occurrence of fatal landslide revealed the strong climatic control on the triggering that instability. Now you can see we have examined the occurrence of fatal landslide in the period of 1970 to 2019. Our dataset suggested that the occurrence of fatal landslide event that increases in the recent year. And now the most likely explanation for this is the maybe rural road building program, which coincide with this increase. Now I would like to talk about the rainfall threshold. Actually, the rainfall threshold, the definition of rainfall threshold is the minimum rainfall that requires to the initiation of landslide. And globally, there are so many methods which
Ananda, can you just
yes.
Wait, somebody is writing in the screen. Can you just stop? Otherwise, we'll find it out, and this will be taken as offensive. Please do not do the annotation in the slide. Please continue.
Okay, this is a highlighter actually.
Somebody was writing something. Please go ahead.
Okay. The rainfall threshold means the minimum requirement of rainfall for the landslide initiation. There are two types of rainfall threshold. First, regional, that is statistical based, depend on intensity and duration of the rainfall during landslide events. And other is the site specific. that is physically based, depend on hydromechanical parameters. Different type of rainfall thresholds are using globally. In Nepal, Dahal and Hasegua in 2008 published a paper regarding regards rainfall threshold using minimum level line of the rainfall threshold. I really appreciate this work. Actually, in 2008 and before 2008, there was not accessible of data, and they collected a huge compilation of the data. Previous study used minimum level line of rainfall threshold. There are only two zones. One is no alarm and other is alarm zones. We use a quantile regression method in this study to make a landslide hazard levels, warning levels. Now you can see in this graph for the minimum rainfall threshold warning level. Now there is just two rooms. One is no alarm, another is alarm. And we use regression, that quantile regression method of different hazard level. And we adapted from this kind of method from Save Land in 2020 and Bowman Gold 2010 and Brunetti in 2010, Rossi et al. In 2012. And this method is robust and resistant against error and outlier. And this method, using this method, we can divide this whole rainfall threshold into four different zones. One is null zone, another is alert, warning, and evacuation. It can be named in different way. So to make the landslide, the rainfall threshold, here we selected 220 landslide from 2000 to 2015 that was selected to prepare a rainfall threshold. Actually, to be honest, this work is incomplete work. This is demo work because we have to, we have to do a lot of work, a lot of things to get the final rainfall threshold. And still we are working on this, and probably after 3 months, maybe we will complete and we will establish a rainfall threshold for Nepal Himalaya. And yeah, the rainfall station of DSM, Department of Hydrometeorological, are very coarse and few are not working. In this case, the satellite precipitation estimates a good alternative to rain gauge, especially mountain region. We used young IMERS rainfall data. Later, we are planning to calibrate with the data of rain gauge station of DSM and other local and private rain gauge station. Now you can see that this is the rainfall that map in different time. Now the IMERS that new SN precipitation data set, and it has a resolution like 0.1 degree, and half our rainfall data can be downloaded from that website. And this is the rainfall threshold, and the rainfall threshold curve is a form of a power equation, that is I is equal to alpha b power minus beta. I is intensity, D is duration, and that alpha is the intercept and beta is slope of what the power law curve. These are the coefficients. And this selection of the method, selecting method of rainfall intensity and duration, then I and D is different. The different researchers selected in different manner. Some includes antecedent rainfall too, and some doesn't include the antecedent. In this here in the graph, the left graph, you can see the method is selected for the intensity and duration. Now here in intensity and duration is taken as like critical rainfall and critical rainfall intensity and critical duration. That is here you can see there is no rainfall for 24 hours. So after that 24 hours, we can start to count that critical rainfall intensity. And similarly, and this is here from here to here, the landslide event, here you can see that is a critical duration. From that critical duration and critical intensity, now we can make a rainfall threshold here. And this rainfall threshold is data that I have already shown that we selected 2020 landslide data. So from that 2020 landslide, we made that rainfall threshold, dividing the 5%, 20%, and 50% threshold lines. And we use the another data like 2013, 2014, 2016, three data from 2017, and three data from 2018 for the validation of the model. Now you can see the more or less this rainfall threshold is validated. Now we can give that nomenclature or naming of that table, like if the rainfall threshold is below 5%, we can then name it like as null. That means no warning will be given to the local authorities or the population. Similarly, was, that is 5% to 20%. Attention is 20% to 50%, and alarm is the above 50%. That is, alarm means there is a great chance to occur landslide in next hour. So therefore the local people must be alert to evacuate the threshold that certain area. Now this kind of that rainfall threshold can be validated using that matrix, the contingency matrix, the contingency table. Now you can see there is a observed event, that is the real database, and that forecasted event, that is the landslide that the point above the or below the threshold lines. From that we can calculate the heat rate and false alarm rate and the area under the curve. The area under the curve is higher is better for the prediction and for the validation. Now I would like to talk the landslide susceptibility. Later I will show you how we can combine this rainfall threshold with the landslide susceptibility. Now the landslide susceptibility is a spatial likelihood. There is a probability of occurrence of danger is the landslide susceptibility. If we say the probability of occurrence of particular landslide type in specific period of time is known as the landslide hazard. Actually, hazard is a temporal. It can be changed dynamic. I mean, it is a dynamic. It can be changed by time. But the susceptibility, it is almost fixed because it's a likelihood occurrence of probability. Now here the rainfall threshold is a triggering factor, that is when, and landslide susceptibility is where. Now we can combine these two, landslide hazard susceptibility and triggering factor, to make the landslide hazard. The lower figure, it shows the rainfall that landslide risk, which is very difficult to calculate and mostly important to calculate for the land use planning. Now, if you follow the different researchers, and there are different types of landslide susceptibility modeling. Like one is expert opinion model, that is sometimes called ASP process. Other is data mining, that is machine learning, probability model, that is frequency ratio and evidence belief function. Similarly, statistical model and physical based model. These are the most used different kind of model. But ultimately, whatever we use, ultimately the method is like this is like an overlay analysis. We will get some value from some pixel, and we will overlay everything from every layer to get the probability of occurrence of danger or the probability of occurrence of landslide. Now I would like to show you some case study. Recently, we have performed a work that is the identification of landslide in Darjeeling district, the far western Nepal. In that region, actually, we use the remote sensing technique. For that technique, we use sentinel image for different year from 2016 to 2019, and other parameters from sentinel image we generate the NDVI, and from DEM we generate the slope, aspect, and curvature. From that different layers, so we combine this integrated using the machine learning, deep neural network, and we can get the landslide that landslide inventory to make the landslide susceptibility map. Now here you can see this is aspect, slope, plant curvature, and other parameters to get the landslide distribution. Now here is the landslide distribution in 2016. Similarly, landslide distribution in 2017 and 2018 and 2019. This is a combined landslide distribution of Darjeeling district. Now you can see the probable density function from that. The landslide area, probable landslide area, and the probability density function, the relationship between this landslide distribution of landslide, it can be defined using this the power law equation. Yeah, I would like to show you the another work. After that, generating landslide inventory, and there are another method also that is field-based method. And we perform this kind of work in the Phewa catchment, which is 200 kilometers northwest of Kathmandu, covering an area of about 1 to 3 kilometers square. We went to field and we collected database from the field, and we also used the similar method that previous I already described, like in Darchula. And after that, we have collected 675 landslides, and we use different parameters for statistical methods like aspect, elevation, slope, plan curvature, profile curvature, and so on. Actually, so many data, it doesn't mean your model will be good. The result will be good. Something we have to discard, remove from that model to decrease the dimension of our database. So here I use the multi-collinearity test, and here we can use, there is two parameters. One is variation inflation, that is VIF, and other is tolerance parameter, TOL. So if VIF is greater than or equal to 10 or TOL is less than 0.2, there is a multicollinearity problem. So we can remove that kind of data. From here, you can see this red is like it's a slope, and the STI, segment transport index, it has a multicollinearity problem. So we remove the STI parameter. After that, yeah, we can see this is the landslide susceptibility model, the final model, and here I use the artificial neural network. Now this can be validated using ROC curve, and actually generally wait and see is the most appropriate validation technique, but it's a time, and so here is we use the training dataset and testing dataset to validate the model. Here now we can see here something I put from Bhushan. This is landslide susceptibility as made in that Phewa, and this is rainfall parameter, rainfall threshold as made in Nepal. So it can be combined using a matrix. Here, if this is rainfall threshold, this is null, watts, attention, and alarm. And this is very high landslide susceptible zone, moderate, low, and very low. So we can make a matrix here, and we can combine like alarm. The rainfall threshold is in alarm, and landslide susceptibility is in high. That means the hazard is very high. So here you can see if the rainfall threshold is going like here in null, this is the hazard condition. It crosses the null line, 5% line. Similarly, it's changing. Now you can see here, this small is a tiny circle is a landslide. After the warning level, it crosses the 50%, there was a landslide. There is a simple algorithm you can make in GIS, and like landslide susceptibility is high and rainfall threshold is alarm. If this is satisfied, then that pixel is very high. If it's not satisfied, so it can change like here in table. So it can be established and forecasting wide area semi-dynamic landslide susceptibility in real time, and the matrix was suggested to combine these two parameters. Now this is my last talk, that is physical vulnerability. And the this vulnerability assessment for eliminated risks, it provides useful information on management of vulnerable areas. And it has different type of methodology. So here we perform using the building type to calculate the vulnerability of any area. That building type is reinforced concrete frame and non-reinforced concrete frame. So vulnerability can be defined or it quantify as from the number 0 if there is no damage, and number 1 if there is total destruction. From 0 to 1 and different database collected from the field, we can make a curve, that is a vulnerability curve. And this is the vulnerability versus hazard intensity. That may be depth or velocity, or it may be impact pressure. So from that curve, now we can make a landslide vulnerability of any area. Here is the simple methodology. First, collection of spatial database and field survey data, element matrix, that is non-RC building and RC building. And this is the physical property, a mobility index that can be calculated in the lab, and volume, catchment area, and peak discharge. Similarly, in that intensity, flow path, velocity, or pressure. Damage, it can be classified into complete, extensive, moderate, and slight. And this is the, if there is damage 0 and their complete damage is 1. From that, we can make a vulnerability curve. For that, we use 11 sites from that in Korea. And from that site, we collected different degree of damage database. And from that, you made that vulnerability curve. This is vulnerability curve for impact pressure. This is for flow depth. This is for flow velocity. And here you can see that relationship. That is, vulnerability is for the non-RC frame, vulnerability for the RC frame. Here, this is the sensitivity analysis using flow R for the landslide that propagation. After using this, now we can find the average flow angle and average value of velocity. So using these values, now we can make a landslide vulnerability. This is landslide vulnerability map of Busan. Now it can be divided into the slight, moderate, extensive, and complete. If we don't have database like in Korea, so what can we do? Yeah, we can make a semi-quantitative method. This is similar to the frequency ratio method. Now we perform this in Socha, near to Bogota in Colombia. From here, we have selected different source zone, landslide area. These are the landslide in abundant mine. And the vulnerability, it can be calculated as area of building in runout zone divided by area of runout zone, which can be later rescaling to make 0 and 1. From that database, now we can make a landslide susceptibility as previous, and it can be validated. And here I assume that the landslide, the cumulative percentage of landslide above 70% is a high zone, which is responsible for the landslide propagation. So I use that kind of area to make the landslide the propagation. And after that, yeah, we can make this landslide vulnerability map. This is the core city of the Socha, Bogota city. Now this is my conclusion. And actually, this is not my conclusion. This is conclusion of Confucius. And he said, when I did not know about mountains, the mountains were like mountains. When I knew something about them, they were no more like mountains. When I learned more about them, the mountains were again like mountains. Thank you for your kind attention. Stay safe. Thank you.
Thank you, Dr. Pradhan, for your very interesting presentation. And this is what we need in the context of Nepal. So can you just close your screen sharing?
Yeah, wait, I have some problem.
No, you just, okay. Yeah. And, now we have to jump from, susceptibility mapping, hazard mapping, and then to the risk mapping, which is the prime necessity for the countries like Nepal and, other mountainous countries. And it is always difficult for the, to set up the threshold value in terms of rainfall. And it's always difficult to measure the vulnerability component while calculating the risk map for the landslides. And especially in the data scarce region, the countries like Nepal and in the Hindu Kush Himalayas, and you have rightly demonstrated the example from Korea and then the Bogota, how different types of data sets can use for this risk mapping and physical vulnerability mapping. So we are very, very impressed from your work in this arena. and some of the good results you have already presented from the Nepal Himalaya, and we are pretty much sure that more will come in next years, and we are very happy that very good researchers like you who are who working in the government of Nepal, so that we are very sure that we will see some differences in the planning process from the government side. So thank you once again, Dr. Pradhan. Please stay with us. I'll take some questions to you later on, and please go through the chat box also, and you can see some of the questions there. Let me see. Okay, so first I will start with Dr. Safiq. Are you there?
Yeah, I'm here.
Yeah, so we have questions both in Zoom and Facebook. So yes. I will take first question from Facebook. From Mandira Shrestha. Thank you very much for your presentation, Dr. Safiq. So while using UAV, unmanned aerial vehicle, for the landslide monitoring, how often flights are required? How will it help in the landslide early warning?
Number of flights usually, flying UAV is sometimes tricky because you need to have a ideal environment, weather environment to control the UAV and also fly get it. So usually, I mean, the more flight are, the better you can have the monitoring. Like you can see how things are changing at higher intervals. So in this case, actually, we took 4 flights. So we took like after in a year, we took 1 flight in January, second was in April, and third was in July, and the last one we took in August. So we took these 4 flights and we get the data. But the ideal would be if you have a more temporal control, like you have a data for the long term, like a couple of years, and then usually you should also take a flight before the triggering event and also after the triggering event. Usually, like if you have a monsoon season, so take a flight before the monsoon and then take out the flight after the monsoon season to see the changes. So in our case, like we take 4 flights in 1 year, and then I would recommend if you have more flights in different years, that will give you more realistic results.
So how will it help in landslide early warning? Can you use UAV for landslide early warning or not?
The early warning will be a bit tricky because because the landslide happen after a big event, like if you have a rainfall event. So flying a UAV during a rainfall, it's nearly impossible. So that will be tricky, but that can at least tell you if you can tell you what is the major trigger, like what's the rainfall is the major trigger or what is the major trigger. Secondly, also it can tell you you can model the cracks, widening of the cracks. You can see the physical feature, how the lesson is behaving after a big event. So you can correlate, yes, you can correlate the deformation of the landslide with some triggering event like the rainfall that was presented in previous lesson. And then you can make some threshold that if you have a rainfall of that magnitude, that intensity, we can expect the landslide. You can use it for the proxy for prediction, but a real-time warning would be a bit tricky, I would say.
Yes, thank you, Safiq. So another question from our presenter, Anand Pradhan. So what are to the Safiq, question from Ananta, but to the Safiq. Okay. So what are the parameters to model soil depth in erosional landscape?
Yes.
Can you just...
Yes, actually we have a paper. I will share the PDF of the full paper, probably the paper that actually we published from these results with all the participants, so they can look at that. For the erosional landscape, we used topography mainly. We used geology was there, geological units we have used. We used terrain slope. We have used also terrain slope and the elevation in that regard. I think this is the 3, and also geomorphology we use that for erosional landscape. So we use 4 main parameters.
Again, question. Okay, thank you. So again, question to you. So what's the resolution of DEM that you have used?
For the soil modeling, we use 30 meter. We use Ostar DM. It's a 30 meter. The 30 meter that is available with the cost. But if we have data of more fine resolution, like nowadays we have a loss at 12 meter available, so you can also use that. That will give you more realistic results, I would recommend.
Okay. So another question from Surendra Saha to you. What is the effect of groundwater level in the model that you have used?
Yeah, the groundwater, we didn't actually check that. What is the impact of the groundwater on the groundwater actually? But I usually expect that if the groundwater is shallow, like you have more water, the actually I can't comment on that. It will be unjustified comment, I would say. Personally, I didn't look into that. And I didn't saw any study actually who actually investigated that. So I would not comment on that.
Yeah,
If
because
somebody,
this is
if
very valid question in the mountains.
Basanta, if you want to comment on that, or maybe Pradhan can comment on that.
No, this is fantastic question raised by Surendra Saha,
Yes.
because the groundwater level and the infiltration and others in the mountainous region, when you have a high thick soil, and then it actually it plays important role for the generation of landslide on it. Dr. Pradhan, do you have any comments on it very shortly? Can you just unmute your...
Very much interested in soil depth modeling.
Okay.
So yeah, we have developed one different model that is internal relief based model. Previously is used like yes model or Z model. So we try to elaborate that, modify that yes model. So actually, if you have that kind of database in erosional land surface, so I would like to use my model in that area to validate my model, So later, yeah, we can discuss.
Sure, absolutely. I think I have samples somewhere. I can share that with you.
Yeah. Dr. Pradhan, thank you. So another question to Safiq from Mohammad Tariq. So asking, as the velocity increases with increase in depth, depending upon the hardness and softness of the rock. So the question is, how the velocity of seismic waves related to the amplitude, which results into high magnitude earthquake at surface. Yeah. Can you elaborate on it?
Yes, this is a very valid question actually. Usually this is what we are seeing, and what actually the literature says, that if the velocity is lower, if velocity is lower, actually you're seeing amplified seismic response, which actually I have given the example of the car when the cars enter what we call impedance contrast. If you use a specific term, it's called impedance contrast, where the material properties of the rock is different than the material properties of the soil. So if the waves enter from the rock into the soil, the amplitude increases, and secondly also the velocity is decreased. And because that's decrease in velocity, the shaking is also increased, and also the timing of the shaking is also increased. And this is actually we have seen in different studies after many earthquakes, that usually in the valley basin where you have a deep soil, the timing, the duration of the shaking was higher compared to the shaking on the ridges, also on the hard rocks. Which also sometimes the liquefaction also happens sometimes, but there you need to have a lot of moisture content. But generally, with a lower velocity, you have higher damages because of the increased shaking also, actually lower shear velocity.
Yeah, thank you for answering this. And another from Mubarak Hassan from Pakistan. Yes. So asking, 2015 cosmic earthquake happened, where it exactly in Balakot backfault or in MBT? What is the actual?
Well, MBT is not it's actually a whole region. MBT is not a specific line. We know fault is not a specific line. It's actually a small region which passes through area. We call it MBT. So MBT is a big, what you call a big region of the active faults in that region. And the specific fault which triggered earthquake is called, some people call it Muzaffarabad Balakot, what he said, Balakot Bach fault. Some people actually name it as a Muzaffarabad fault. But the name is different, but generally it's the same fault. Actually, people name it differently. But it is still part of the MBT. So okay. MBT is a big region, and this is a specific fault within that one region.
Yeah, this is one kind of discussion always in the Himalayas, whether this fault and thrust are zone or a single line. In Nepal, sometimes somewhere people in Nepal Himalaya say that this is a single line MBT and MCT is a zone. And in the similar in India and Pakistan, Nepal, yeah, it's always hanging discussion, because it varies from Eastern Himalaya to Western Himalaya.
Absolutely.
So you have to work more detail on it. So another question is, Shravanti, with satellite data will be used to map the landslide accurately?
Well, it depends on the money, I would say. If you have more money, you can map them very accurately, right? Generally, the research and the literature support that if you have a data with higher resolution, the accuracy will be higher, right? Normally, nowadays, we can see people are also using UAVs. Why? Because it has a extremely high resolution, so you can see even the small scarps. If you can map them. But if you go for but the cost would be higher. Actually it's a cost accuracy continuous balance. You have to keep that balance. If you have a higher cost available, you can go for higher accuracy. You have to buy other UAV to fly the data to get the very high resolution data, or you can also purchase the spaceborne high resolution data to get more high accuracy. But if you go for the relatively lower resolution sensor, like nowadays we have a Sentinel available free of cost, we have Aster available free of cost, Landslides is available. There, yes, the accuracy would be slightly lower compared to the high resolution data. So it's a mainly depend on your budget, also depend on your interest. What is your interest? If you're looking for a very small landscape, a very specific small area, surely you have to go for a very high data, like UAVs are high resolution data. But if you're working on the regional scale or a whole country level, the Sentinel will also give you best results, I would say.
Yeah, this is another important thing we have to discuss in landslide research, because some people say that if we don't have other data and high resolution, it's useless to use the high resolution GM. For example, the geology and the other land use and others. If we don't have a really good one, and if you interpolate or extrapolate the data, and if you, although you have a very high resolution GM, I mean, it doesn't make any sense. And so there's a still a discussion going on which resolution shall we or do we have to use actually for prediction or modeling the landslides that we can use for the landslide research. So another question should be to you also, Dr. Safiq. So Mubarak Hassan, how to mitigate landslide without triggered by rainfall or infiltration? So this is more fundamental question, I think.
Yeah, the mitigation is, we cannot stop landslide. That will happen because of the reason that I mentioned in my first slide. We have active catalysts there. We have frequent earthquakes. We have fragile slopes. We cannot stop people by living in that area. So landslide will happen, but we just have to be prepared for that and try to minimize the human interference, because sometimes we have seen in northern Pakistan that human actually playing a very also bigger role, like building a road into that, and also making some activity like excavation that can minimize that. But completely stopping the landslide is impossible. It's a natural phenomenon. It will happen. It will happen. You just have to live with them. But you don't have to live in the area which are high landslide risk area, or high landslide susceptible area. You just have to stay away from them. You don't have to build a road passing through a very high active landslide. So you just have to avoid them. So you just have to be prepared to stay away from the landslides which are very active. But completely stopping them, it's I would say it's impossible, because it's a natural phenomenon. It will happen. It's also balance between the environment. The landslide happen because of that. So it's not balance. It will happen, I guess.
Yeah. I think you have addressed the question from Teoku Muklis also. It's the same thing. So another, again, fundamental question, how to distinguish the landslide triggered by earthquake or rainfall? So how you differentiate the earthquake triggered landslide and rainfall triggered landslides?
Yes, this is also, you just have to look at the timing when the landslide happened. Usually, if you don't have a landslide and it has happened soon after the rainfall, so it means it is triggered by the rainfall. But for the earthquake, you just have to compare the inventories of the before the earthquake inventory and after the earthquake inventory. The earthquake which are triggered by the the landslides which are triggered by the earthquake, they are co-seismic, triggered. Like if there is a landslide which were active before the earthquake, triggered by rainfall, but other event, it's still present after the earthquake, surely. So you can't say that it's triggered only by the seismic. So you just have to look at the timing, like what time the landslide actually triggered. So then you can tell that if it's triggered by the rainfall or by the earthquake.
Yeah,
Like in case, like in case, sorry for cutting you, but like in case of Muzaffarabad, we know that before even the earthquake, there were lots of landslides. There were many big landslides in that area. Like this, there were landslides in that area. But after the earthquake, we saw landslides which in the area, which were landslides safe before the earthquake. So there was no landslide in that area before the earthquake, but after the earthquake, we saw lots of landslides there. So these are the landslides which were purely triggered by the earthquake. But the other landslides which were also present before, they might be triggered by the rainfall, but they got more activated by the earthquake.
Yeah, thank you, Safiq. And maybe on rainfall triggered landslide, we have some surface hydrological features within the landslides, and that we don't find in the co-seismic landslides. So I stop you here, and I'll back to you again. Now I will start with Dr. Pradhan. So Dr. Pradhan, are you there? Okay. So I'll take one question from Facebook. So from Mandira Shrestha, thank you for your presentation, Dr. Ananta. Glad to see the use of IMERG data for landslide prediction. Have you validated the results? In middle mountain areas, SRE is found to have challenges in correctly estimating rainfall. Have you applied any bias correction?
Thank you.
Mandira Shrestha.
And AIMERG data that was already bias corrected from approved data. So now the ongoing is like they surely bias corrected with gauge data, the real station data. So later on we will correct it with that station data.
Okay, thank you. Another question from Deoraz Guru, sir. So he's asking, Dr. Ananda, how well were
I cannot hear you.
Landslide mapped using automatic. Dr. Pradhan, do you hear me? Hello?
Can you say one more time? I don't know what something is wrong here.
Do you hear me now?
Yeah, yes.
Okay. So he's asking how well were the landslide mapped using automated approach, any accuracy level or indication?
No, yeah, we can actually, what I presented, we can identify landslide using the sentinel data and other parameters. But yeah, we have to validate this. I use deep neural network. So that is machine learning, the advanced machine learning algorithm. So it can pick now it can pick that realistic data that something says in that the terrain, it can pick correctly. But we have to validate that. And now we can validate this data with the Google Earth. So I use first the 100 or 200 Google Earth. That extract data from Google Earth. First, I drew the data, the polygon from Google Earth, and I made it 100 pixels for each landslide, and that is treated as a trained data. So after that training data, now I apply in deep neural network on the model, and after that I use the 90% accuracy data to extract the landslide. So yeah, it has a very good result. Now we are using in province level. So after that, now we can say, okay, this is highly validated and it's not validated. So yeah, This is first attempt.
Okay, yeah. Thank you. There are two questions from Ram Gopal Kharbuja, sir, for you, Anand.
Yes.
Sir. So the first one, is your method applicable for the early warning of landslides? One thing.
Yes, yes.
One question. And the another question is that, can you integrate present rainfall forecast to landslide forecast based on available real-time rainfall data in Nepal?
Yeah, this can be used for rainfall landslide prediction. Of course, I made this the model to predict the landslide. So we can. This is now this data is from whole Nepal, and I try to make a threshold for whole Nepal. But sometimes it is not applicable. So I would like to go like for district wise, because we have plenty of data now. So I would like to go for district wise or the province wise. After that, now we can link this rainfall threshold, the east rainfall threshold for every province or district can be linked with the mobile, providers. So after that rainfall, if it exceeds the threshold, the mobile provider can give the warning to the mobile holders. So this can be used in the landslide trigger or landslide early warning system. And for the second data, could you ask again? Could you repeat that second question?
Yeah. So the second question is, can you integrate present rainfall forecast to landslide forecast based on available real-time rainfall data in Nepal?
Yes, sure. We can do that. Now we are moving toward that, and so this is our first step. After 3 months, 4 months, we will able to finalize the final threshold, and after that, yeah, we can integrate with any other data. Yeah, sure.
Okay, thank you, Dr. Pradhan. So another question is from Ramesh Gautam in Zoom chat box. How early warning regarding landslide hazards could be effectively implemented in sustainable way in Nepal? So further, most of these hazards are in remote areas, and people living in such areas have less access to the communication as well as could not understand such advanced technology. So what should be the government strategy to map the landslide risks in Nepal? Can you elaborate on it?
This is very, very crucial the question. Everything is that inside this question, Actually, we have to start from zero, grass level. Now, if we make an early warning system, and we are it's like a using masks during the COVID. Everybody has that mask, but nobody is wearing that mask properly. Exactly, landslide susceptibility or landslide warning system is exactly like this. So first of all, the government should include that disaster and the mitigation of disaster that can be course in school level. After that school level, the students start to know how to treat with the disasters, how to treat with the landslides. So I'm surprised to know that in Korea, 2 grade standard student, they study about landslide, 2nd grade student. But here, I studied landslide in BSc, it's 4th or 3rd year in engineering geology. So this is the gap. So let's start from zero. Then we can, in 3 year, in 4 year, now we can make a good plan, and we can, that the result will be very good. Yeah, I believe that.
Yeah, thank you. So another question from Dharmo Preti to you. Could it be possible to make our mountain, hill, and a particular landscape resilient to that of rainfall threshold in given time?
No, first of all, look, landslide is natural phenomenon. So we have to live with landslide. We have to love landslide. Yeah. So that means, yeah, we have to treat correctly the landslide. So that the hill slope, which is resilience from landslide, if we want to make is almost impossible for the large areas, because landslide is it happened. What is the definition of landslide for the general layman in the layman level? Any unstable material to become stable, the landslide happens. So Nepal Himalaya is rising, materials are unstable. So that unstable material, it will be it need to be moved from higher level to lower level to be stable. So it's a little difficult, but yeah, little catchments it can be.
Yes, thank you. So another question from Meena Adhikari. Is it possible to develop an early warning system for Nepal?
Yes, yeah, I am talking. This presentation is, it's focused on, yeah, we can make early warning system. We can make a dashboard.
Yeah, thank you. I'll add on it. We have already tested physical-based landslide early warning system.
Yeah. I have forgot to tell you. Yeah, I have forgot to. Yeah.
Yeah, in Dolaka.
There is landslide susceptibility, that warning system. There are three types of warning system. One is statistical, which I presented. Other is physical-based model, which depend upon the soil moisture, corresponding rainfall. And third is what Professor Adhikari, he did a tremendous job. Yeah, very fabulous work in Nepal. He installed a very cheap and effective system for a particular known landslide. Yeah, congratulations.
Yeah, thank you, Dr. Pradhan. And it's already published in scientific journal, and it worked in Dolaka in Sundravati with the help of FAO and Ministry of Forest and Soil Conservation, Nepal. So if you are interested, we can share our paper to you all about the low-cost early warning system. So another fundamental question from Ramesh Tuladhar. So if you have such kind of technologies, why Nepalese people are being killed every year due to this landslide? Dr. Pradhan, can you enlighten us on this?
This is a very difficult question. Yeah. Each and every day we are inventing new medicines. Oh, we are dying. Actually, yeah, we need a very good strategy, a very good commitment to prevent the landslides. If we see from in my graph also, I saw in last couple of years the number of landslides is increased tremendously, 100 times increase. Same thing was happening in Hong Kong, in Korea, in Japan a few decades ago. But this day you can see the tower is lowering. And actually, in Korea also, this day there are so many landslides that event is occurring there. But that is like, if you see the casualties, this is comparatively previous years, it is too low, previous decades. In 2011, that there was so many casualties. But today the number of landslide is higher, but the casualty is low. This is very crucial and tricky question, and we have to ask to someone who worked for government for a long time in landslides, and yeah, we can get a proper answer from him. And we can get the experience from him, and we can go further.
Thank you, Dr. Pradhan. Very diplomatic answer. And definitely days will come when we can combine all these recent technologies for the disaster risk reduction in the Nepalese Himalaya. And another question from Ramesh Tuladhar. Also, I think you have already covered up that with the question from Ram Gopal Kharbuja, sir. So I'll move to another question to Dave Bhatta. Question to Ananta. Would you please provide the information on landslide early warning system that we have already talked and its effectiveness? So Dave Bhatta, if you are interested, we can share our paper so that you can study that. So another question from Mubaris Hassan, I think it's question to Dr. Pradhan. So what about the plantation, or no, it's for the Dr. Safiq. So I'll come to you, Dr. Pradhan, later. Dr. Safiq, so So question from Mubar is, what about the plantation or vegetation on slope in order to reduce the rock and debris flows? Can you just elaborate on it a little bit?
Yes, they are contributing to reduce the debris flow specifically. Uh, also the rock flows. Like this is what we actually seen in Muzaffarabad, in the area where actually we worked after the earthquake. That because of the increase in vegetation, we see also landslide number is being reduced, and also in most of the landslide mitigation plans or landslide risk reduction recommendation. People also recommending to plant the vegetation there, because that will actually the roots will actually increase the shear strength of the soil, and that's what also it will also reduce the erosion. That will also contribute to the reduce the debris flow and also the landslides. They will surely contribute. Yes.
Yes, thank you. Another question from Rahul Saik. Yeah, I think talking about the early prediction of earthquake. Yes, there are some thing the animal, used or their sign used in the past, but this is not 100% early warning, and somewhere we had false,
Yeah.
signals also. So
it's not proven. It's not proven. Actually, it happens sometimes, but it's not happen all the time.
Yeah. So another from Alan Rose, can you use the NDVI for landslide susceptibility assessment? Yes, I think Safiq has already demonstrated that. From Robin Sharma, yes, we didn't have natural disasters, we have only natural hazard. So with the combination of anthropogenic or human, then it will turn to natural disaster, of course, or only disaster, not natural disaster. So another question, I think from Rajan Gurung in Facebook, you have already answered the use of bioengineering techniques for landslide mitigation. That is one of the best techniques in Nepal, Himalaya. In 90s, when we had built our Dharan Dhankuta road, it was the best site for using the bioengineering techniques. And Krishnavir, which is one of the most problematic landslide in the Nepal Himalaya, was actually established by using the bioengineering works. That's a very good thing from Rajan. And so to question to Dr. Pradhan from Arjun Prasad Tiwari, Anand sir is expressing as DRR phenomena is on the very poor and we need to work from the zero. That it's been many years people are talking about DRR. How can we believe that someone like you in days to come would also say that they are working from zero?
I think it will take 1 or 2 years to prepare the answer of this question.
Thank you, Ananda. Yeah. So, yeah, I think we'll close the question now, and I have some particular interest and discussion with both of you. The first thing I really want to stress that to Dr. Pradhan, that we're very happy that you have provided really good opportunity to discuss another thing. Now we have to shift from landslide hazard or susceptibility to the risks. And to do that, we have to motivate our young researchers from this region, not only from Nepal, but also from the other countries in the HKS region, so that we can develop whole landslide threshold or prediction or early warning in the whole HKS region. And that let's work on this regards. And later on, maybe Suraj Gautam will explain a little bit. And Dr. Safiq, and it's always happy to see you and when you are doing presentation, and we're working for a long time together, and we hope to continue our research in days to come, involving our young generation to understand these Himalayan dynamics in terms of this young seismically active mountains. And landslides are one of the major hazards, not only in Nepal, but also in Pakistan, India, and Bhutan. So, and also in Afghanistan, also in mountainous region around the globe. And so thank you very much for your, full presentation, and we are very, very happy. So now, do you want to say something, Dr. Safiq, at the end before I hand over this for platform to Suraj?
Oh, I just want to thank everyone, the participant also, especially because they're here. We're happy to share our stuff that we're doing. And I'm also looking forward for developing collaboration also. If somebody is interested to work on stuff that we are doing, I'm willing to help. If there's any query, you can send me email. My email is already given before that. I can also share it now again. And thank you very much again, Basanta, Suraji, and the Institute for this webinar. Thank you very much again. Thank you.
So, Dr. Pradhan, do you want to say something at the end?
Yes, thank you so much for having me here. And yeah, Basanta and team, you are doing tremendous job. And yeah, for new researcher, okay, from here, I would like to say, I would like to invite the person who are interested in to work in landslide susceptibility and landslide threshold, rainfall threshold. You are always welcome, and you can get my email or Facebook, or yeah, you can find me in ResearchGate and email me. Thank you. Yeah, thank you.
Dr.
Thank you, Dr. Pradhan.
Okay.
So now, yeah, please, Suresh, now you close the session.
Okay, thank you so much, Dr. Prasanta, uh, for the excellent moderation and making this webinar session very much lively. It is always pleasure hearing from you. And yes, we had a really interesting session, especially myself also being a Geohazard researcher. I found this session very much fruitful, and IHRR is also preparing some specific initiatives to contribute in this Geohazard risk assessment. So hopefully we'll have some good collaborations in the days to come. We'd like to thank Dr. Muhammad for the wonderful review of the works that has been done. It was really interesting to see your works on temporal changes in the co-seismic landslides, and it was also really interesting to see the use of that time-lapse camera for tracking the temporal deformations through the real-time monitoring of landslides. I believe these presentations has really been helpful to our participants. We'd be really happy to work and collaborate in the days by making the use of such kind of frontier technologies. Similarly, we'd also like to thank Dr. Ananta Pradhan for sharing his works on rainfall thresholds and landslide susceptibility mapping. We had case studies from Darchula districts, Fewa watershed, and also it was really great to see the use of rainfall threshold warnings and the shallow slide susceptibility in Busan, Korea. We are really delighted to hear your works on physical vulnerability and risk mapping. And the Q&A session was also really informative with a huge number of quality questions. We tried our best to address all of these questions from our Facebook page live and the Zoom chat box. In case you have any further queries, please feel free to mail us at info@inhrr.org. I'd also like to convey my big thanks to all of our organizing team, speakers, session moderator, our distinguished guests and participants for participating in this session. The session was thoroughly informative and was technical and was really interactive. So we'll be sharing the recorded session of on our YouTube channel, and the links will be forwarded to the registered email. We have a long way ahead, and we'd be happy to collaborate and coordinate with the number of organizations to aim for the sustainable risk reduction. Also, I would like to share, we have a scheduled webinar series on geoscience for sustainable development tomorrow, that is August 9 at 8 p.m. Nepali time. So the topic is importance of optimizing geodatabase for developing countries and its application for disaster mitigation strategies by Dr. Rama Mohan Pokhrel, who is a senior research associate at the Department of Civil Engineering, University of Bristol, UK. So we'd also like to mention that IHRR would be really more than happy to collaborate and organize this kind of relevant webinar in the days to come. And with this, I would like to sign off from our session for today. Thank you, everyone. Thank you once again. Namaste. Have a great time.
Thank you. Namaste. Thank you.
Stay safe.
Namaste. Bye-bye. Stay safe.